that for the duration of the talk, for security reasons, you will not be able to unmute yourself. You'll be muted after the talk is over, so you can ask questions. Thanks. Right, you're ready to go.
Okay, very good. Thank you so much. Thank you for the invitation. I was going to tell people, like, feel free to interrupt me if you have questions. Thanks, but I guess not. But in any case, I'll be looking forward to many questions and comments that you might have. So the reason why, maybe you can also write it in the chat if you do have questions. So this talk is going to be bringing together some very old concepts that are very common in the string theory community, such as symmetric product orbifolds. But at the same time, it's going to be bringing new perspectives of ADS-CFT. So I'll be using jargon from the past and from the present. And so that's why if some things are out of context or not clear, please let me know. The other thing about this talk is that most of the things that I'm going to describe and I'm going to explain are motivated by ADS-CFT. And so the perspective that this program has and the papers that we were writing in this area is how to define the theory of gravity on ADS via the CFT. And for that reason, many of the things that I'm going to do are inspired by gravity in ADS, but there's not going to be any gravity at all. This is going to be a talk about CFTs and really trying to understand what are the properties of CFTs that make them holographic. So with that said, let's dive straight into symmetric product orbifolds. So the main character of this talk. So let's just define it. So the most dry beginning. So what is a symmetric product orbifold? So basically, it's you tensor n copies of a unitary and compact CFT. It doesn't have to be compact, but for the purpose of this talk, I will consider compact CFTs in 2 dimensions. And so you grab your favorite CFT, which we will call the seed theory. You tensor it n times, and then you orbifold by the permutation group Sn that appears. Okay, and that's basically the definition of the symmetric product orbifold. Now, one of the basic features that comes out of this is that orbifolding in this context is very similar to gauging, roughly speaking. So like at the basic of like what shows up in a symmetric product orbifolds, there's 2 types of states. There's an untwisted sector, so basically states that are invariant under the permutation. And then you also have twisted sectors that are basically labeled by conjugacy classes of this permutation group. Okay. So for now, this is all that you need to know for symmetric product orbifolds in terms of its basic definition. Now, why are we studying these theories? So why am I diving into this very specific and seemingly very specialized type of conformal field theories in 2 dimensions? Well, there's an appeal to this type of constructions. They have a lot of mathematical and analytic control. So they're a type of conformal field theories that we can study very well. One example that might be familiar to many of you, it's their generalized partition function that is described by the Dijkgraaf-Moore-Verlinden-Verlinde formula, which will show up later on as I present some discussions. It's also very familiar. Symmetric product orbifolds appear quite prominently in string theory, in particular in the context of the D1, D5 CFT. At its orbifold point, it's described by, well, the orbifold point says it's described by symmetric product orbifold. Now, more broadly, outside of the realm of string theory, if you want to study these theories more generically, besides some very specific string compactification, they're quite universal. So regardless of the seed theory that you have, they have a large M behavior that is quite robust, and we're going to review what those robust features are. And from that point of view, this very robust universality gives us a lot of compelling features in the context of ADS-CFT. Okay, so they comply with a lot of the things that we expect that are true and interesting about the correspondence. Okay, now what I want to do today is basically not highlight things that are universal about symmetric product orbifolds. What I want to do is discuss non-universal properties. So properties that you might thought that all of these conformal field theories share, and they will all lead to the same patterns. But actually, I want to demonstrate that there's different classes of symmetric product orbifolds, some of them complying with laws or beliefs that we have about the correspondence, and some of them that don't quite. And this is where my stranger things are going to show up. Okay, so there's sometimes during the talk there will be a little ghost, and I will make reference to that little ghost. It's a like strange behavior that is bothering me, and maybe some of you will give me comfort and tell me, Alejandra, it's all fine. This is fine. You don't need to worry. It's okay. Or maybe some of you will be as confused as I am and try to explain to me like what's going on. So so then the thing that I want to then divide, this talk is then going to be divided into two parts. Depending on how things go, I might go very quickly through the second part, but let's talk about, let me just give you a very brief overview of how these two portions of the talk will go. So we will first talk about the classification of symmetric product orbifolds. So here's where I'm going to highlight what are differences between them, despite the fact that they might look all very similar. And I'm going to, in this context, give you very precise and new examples of CFTs that might be holographic. Okay. Now, this is based, so here I listed the most recent papers on this topic, the one, and this one that came about a week, no, 2 weeks ago, I don't remember, but very, very recently we posted a paper on this, but it's also based on prior work from this past couple of years. And I want to, at this stage, highlight the most junior people in the collaboration so far. So, well, there's very recurring names like Alex and Christoph here showing up, and Nathan. But I want to highlight my PhD student, Susanna, and Yilda, who just finished her master's degree, and they were incredibly important in doing this. So they're two very talented young scientists, and I hope you remember their names and keep track of their developments. They're really, really great students. I'm very proud of them. So, but this is the flavor. This is going to be the flavor of this first part. Now, for the second part of the talk, we'll see how much time I will have to go into this, but it's basically then understanding what happens to deformations of symmetric product orbifolds. And the main question, the reason why we're deforming them is because we want to understand if we have sufficient conditions to basically coin a CFT as holographic. Here, I also want to highlight Luis Apollo, who's a postdoc at the University of Amsterdam, and him and Susanna were like amazing. Like the results that I will show you, all the credit goes to them. These computations are not easy to do. I don't believe I would have been able, or it have been taking me many, many years to do them all by myself. And the two of them were quite impressive. And so if you want to know more details about how those computations were done, or you're just curious, I want to highlight again the two of them. Okay. So very good. So with that said, I think I'm ready. So we're going to start diving into this land of symmetric product orbifolds and their classification. So let's go through the first part of the talk. Okay. So what's going to go on? So let's first talk about what do all symmetric product orbifolds do, and they all do very, 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 very well. Okay. So what are like 4 properties that they all are fantastic are? So here I listed, these are my 4 favorite ones that they do pretty well. And I give you some references. I'm sure I'll be missing lots of references in this talk, but just to give you an idea, these are very old subjects with a lot of work on them. Now, out of these 4 properties, let's first focus on the first 2 of them. So the first 2 properties are properties that at least I particularly like. They're very nice. So the fact that correlation functions comply with a large N factorization, it's a very nice property that tells us that, yes, this is a good place to study ADS-CFT. And in the context of black hole physics, if you care about like how to model a black hole from the CFT point of view, one of the requirements in the context of ADS3 CFT2 is that you need to have a Hawking-Page transition. And one of the things that has been shown that any symmetric product orbifold that has a compact spectrum basically will have a Hawking-Page transition. Okay, so you don't need to require, there's no restriction on what the seed theory is, so you don't have to impose any restriction on the individual component that you're tensoring by. All of them will have the Hawking-Page transition, okay? So those are great, two properties that are great, very favorable in order to give it a gravitational interpretation. Now, there's two additional properties that are also extremely, extremely robust that you will never be able to get rid of because it's due to the orbifold structure. And the two properties that I'm like not so keen on are the fact that you always will have higher spin currents due to the orbifold structure. I'll show you in the second part of the talk how these higher spin currents look like. They're easy, conceptually, they're very easy to build. Their expressions explicitly, they're not so illuminating, but in any case, you have an infinite tower of higher spin currents in this series. And the other thing that Christoph showed back in 2011 is that the partition function, if you just grab the partition function that counts all states in the theory, it universally has Hagedorn growth, okay? In the light part of the spectrum. So not a Hagedorn growth here, that's very important that I'm referring to the light part of the spectrum. We'll talk more about this in a moment. But basically, the perturbative sector of the theory behaves like a Hagedorn-like spectrum. And from this point of view, based on these two properties, like if you wanted to understand, okay, so what is a symmetric product orbifold dual 2? You would say that it looks like a tensionless limit of a string theory, okay? So, or it looks like a higher spin gravity. That will be the dual, okay? Of course, in very specific examples like D1, D5, the work of like Matthias Gabriel and Rajesh Kumar and Lawrence Eberhardt, they have been establishing this very, very precisely and very carefully for all types of spectrum of self-operators, also Parati with Klebanon and Giribert. There's been a lot of work in trying to establish this very, very, very precisely for D1, D5 CFT, which we all believe, but okay, the details are important as well. But in general, like if you grab any of these theories, even if they don't have a string compactification attached to them, you will kind of think of them of like, yeah, this looks like a tensionless limit. Okay, and these are the properties that I want to get rid of. Okay, so these are things that, from my agenda, my point of view, I'm not super interested in constructing examples of ADS CFT that have all these higher spin symmetries and this Hagedorn-like growth. I want to try to understand from which point of view these theories could lead to a strongly coupled regime with a supergravity-like interpretation. And so from that point of view, what I will care about is what is the moduli space that these theories admit, okay? So I want you to think of like the symmetric product orbifold as being one point in my cloud, my very ill-defined cloud of that I will be calling the moduli space, which is basically a set of exactly marginal deformations. And so usually the way we think about symmetric product orbifolds is that they correspond to a weakly coupled point of the theory, where basically in the known examples, it's where the string scale is very similar to the ADS scale. But what we want to do is turn on a coupling that I'll call lambda, and turn it on by turning on a marginal deformation and get to hopefully a point, a strongly coupled point, where you have a hierarchy between the string and the ADS scale. So most states become very, very massive, and then you have at low energies, just the supergravity like spectrum. Okay, so the basic question that I'll be asking is basically, first of all, which of these symmetric product orbifolds, if you give me a seed theory, when do you have such a moduli space? And if you have a moduli space, when can you establish that a strongly coupled point exists? So how can you infer some properties about this point? And this is something that we're pretty bad at. Just I'll tell you right away, like we all believe, for instance, for D1, D5, that this point exists because of various indirect reasons. But from a conformal field theory point of view, it's not clear that this point exists. It's not obvious, right? And so part of our endeavor is trying to understand, okay, what are the clues? How can you build evidence towards the existence of this point? Okay, so yeah, so this is pretty difficult. I'm not going to claim today that I have managed to prove the existence of this point, but what we're going to do is we're going to impose necessary conditions and try to see, based on some set of necessary conditions, which of the symmetric product orbifolds comply with these conditions, okay? So we'll impose points here to first establish that this exists, and given that the cloud exists, that there's some point in moduli space where there might be a strongly coupled point. Okay. So that's the basic idea. Very good. So what are our and let me just say two more things. So when we talk about this strongly coupled point, here is where I want to specify, I'll be using a lot this term of holographic CFT to illustrate the strongly coupled point. Of course, a CFT, if you're a strong believer of ADS CFT, you will say it's always by definition holographic. But what I mean here when I use the term holographic CFT, I mean it's a strongly coupled point where some of the basic requirements are that you have a large N, that you have a sparse spectrum, and you have a large gap in the spectrum. These are some of the requirements that we know a holographic CFT should comply with. And basically what I'm trying to do here is try to see what is the intersection, how based on some space of CFTs, how can I get to those holographic CFTs? And here, just to be clear, also because of the way that I'm setting this in terms of a moduli space, we'll be looking at supersymmetric conformal field theories. I don't have definitions of these concepts in the absence of supersymmetry. So, and I think most of the things that I've said so far, I don't know how to apply them in a context that is not supersymmetric. But okay, very good. Now, okay, so now let's move on. So let's talk about what are these necessary conditions. So what am I going to be imposing on the symmetric product orbifolds? So the first criterion, so there will be two of them. And the first one is basically, I want to have a suitable moduli. I'll tell you what type of moduli I'll be looking for in a moment. So I want this marginal deformation to exist. Otherwise, there's no place that I can deform to, and I will always have these universal properties. The second criterion is a sparseness criteria. So as we said, these holographic CFTs will have way less states than Hagedorn, than a full string theory. So most of the states will be massive in this context. But the elliptic genera is quite a nice object to impose this condition because it's, as we'll review, it's blind to it. So we'll impose a sparseness condition on Porter BPS states and basically see if this gives us some signal that the strongly coupled point appears. Okay, but regardless of if you don't want to think about ADS CFT, this is basically the two conditions that we're going to be imposing, that we're going to use as a way to classify the theories. And based on that, naively, like you have basically four options of what a symmetric product orbifold could do. So what I will call type 1 theories are theories that obey both criteria, meaning that the moduli will exist, the suitable moduli for the deformation will exist, and they will meet a sparse condition on the elliptic genera. Criterion type 2, it's that only the first criterion is satisfied, but not the second one. Type 3 is that neither of these are satisfied, and type 4 is one where only criterion 2 would be satisfied. Okay, very good. So with that said, let's go first through the criterion number 1. So what is this moduli? What is this marginal operator that we require. So it's not any marginal deformation. So if you have a CFT, and in particular a symmetric product CFT, there will be very, very different types of marginal deformations. You can have marginal deformations that live already in one of the copies. That's not what we're interested in. You can also have deformations that will be in the untwisted sector. I'm also not interested in that. What I'm interested in is a marginal deformation that complies with these three properties. So the first one is that it's half BPS. Okay. Why do I care about this? Because the reason why I will care about the operator being half BPS is because then supersymmetry will assure to me that it's protected. Okay, so then I don't have to worry as I do deformations that I have to redefine the operator. Okay, so this is a very nice property to have. The second is that I want it to be a twisted, I want it to be in the twisted sector. Why do you want this thing to be in the twisted sector? Because operators in the twisted sector, if you deform by them, so if you turn on in the action a twisted operator, what it will do very quickly is break the orbifold structure. And if you break the orbifold structure, you intuitively, you will get rid of all these higher spin currents. So that's why you intuitively think, okay, I want something twisted. If you turn on an untwisted operator, it might be that some of the higher spin currents get lifted, but not maybe all of them. So this is like the basic mechanism, how you can see that all these higher spin symmetries that I had will get rid of if you have a twisted operator. And then in terms of its normalization, you want this to have a component that is single trace. And this is so that when you take the large N limit, you could have also multi-trace twisted deformations. They exist. I'll show you in examples that they are part of the moduli space, but it really, in order to deform the theories, you want this to be a single trace operator so that it has the biggest effect in all of the operators that you have. If you have a multi-trace deformation, then it will not have the imprint of like lifting or giving anomalous dimensions to everything that it could in principle. Okay, so these are the three conditions. So when I talk about moduli, and I talk about like the existence of this marginal operator in the context of this criterion one, I'm thinking that the operator obeys all these three conditions. Okay, it's not strictly speaking the definition of a moduli space, but it is going to be the working definition for the talk today. So when I say moduli, I'm butchering a bit the word, and I do mean an operator that complies with these three criteria. Okay, very good. Now, the second criteria, so this sparseness condition. So here's where also, again, supersymmetry will play a prominent role. So what I'm going to do is look at the elliptic genera. And the reason why we're going to look at the elliptic genera, because it's a quantity that is independent of lambda. Okay, so it's protected along the moduli space. So you can compute it at the orbifold point, and it should tell you something about the spectrum in the entire moduli space. And this elliptic genera, so here I wrote the definition for basically a single CFTC. And this is where the DMBV formula enters. So if you know the symmetric product orbifold, if you know the elliptic genera of one instance, then the DMBV formula, what it nicely tells you is how to build a generating functional that captures the elliptic genera of any n instance of the symmetric product. So this formula over here is something that I love. I love product formulas. They're very, well, I learned how to manipulate them, so now I find them very easy to use. But this is the analytic and the mathematical control that we achieve in this context, and they're very, very closely related as well to paramodular forms. And so
I have a question.
Yes.
Yeah, we have been told we can ask questions. So is this Z like a grand canonical partition function, or is it more sophisticated?
No, it's a grand canonical partition function. So it's your first version of averaging. So we're averaging literally here, you're averaging over theories. And you're using, so usually, and nowadays the concept of averaging, it's done in terms of the Tove coupling. And here we're averaging with respect to n, to G Newton. The thing that is funny is that this is very old in the context of string theory. This is what people would have called, oh, you're doing third quantization from the point of view of the world sheet. But it's from a holographic point of view, from the perspective of ADS CFT, you're basically averaging over G Newton. Now, the thing that is nice about this, and I think it's what makes these instances very powerful, is that it makes very clear what it means to take a large n limit, because you're taking an ensemble interpretation of n, and then making an asymptotic expansion in n is something that you can define very precisely mathematically from the point of view of this generating function. So this is quite nice, but yeah, you view it as like an ensemble over n, and then you want to extract the large n behavior out of this formula.
Is there any relation between the large n and the n equal 1? I've seen similar things happens in
there is, in the sense, this is something that yeah, so a lot of them, it's because of how the powers come in here. So, and this is why the formula is very easy to manipulate. So all the power, this number here is basically the number that appears when you just have one copy.
Mm-hmm.
And so in some sense, the single copy is governing a lot what it trickles throughout. And so when you, for instance, when we extract information about just the light states, and so if you want to tell me like, oh, how many vectors or hypermultiplets does your theory have, like in the supergravity limit, they're all controlled by the n equal 1 data. And so these numbers here are quite important. And then if I have a supergravity match, they will tell me about the matter content of that supergravity theory. Yeah.
Thank you.
Yeah. At least in the cases like of K3, that's how it works. So the number like 24 shows up a lot, and it's because here there's a 1, and then you always have like C over 24 and stuff like that, and then it tells you like, you have X number of like vector multiplets in the ADS 3 times S3 times K3, let's say. And it also affects the log corrections of the black hole entropy. So when a Shok-Sen computes logarithmic corrections to the black hole entropy, the logarithmic corrections are basically also controlled by that, but the data of the n equal 1 theory. So yes. Okay, now, so the nice thing about this quantity is that it's independent of lambda. Of course, it doesn't count all states in the theory. It counts quarter BPS states, and moreover, it counts them with a -1 to the f. So it's not all quarter BPS, but it's assigned counting. Sorry, but it will tell you something about a lower bound of the total growth. So this object, as I will illustrate in some examples, in many examples, it already has like Hagedorn growth. You might have thought that the -1 to the f cancels many states, but I can give you an infinite list of elliptic genera that have Hagedorn-like growth. And so if you have that type of Hagedorn-like growth, then it doesn't care that you have a deformation. This thing is protected. It means that it's Hagedorn everywhere. And so then the partition function also doesn't have any hope to be lowered. But now, if this thing is lower than Hagedorn, then you will have some hope that the partition function will also follow suit. So it gives you an indication that there might be some lowering if you turn on lambda. But again, if this one doesn't comply with it, or this one over here doesn't comply with it, then there's nothing else to do. You can just move on. Okay. So, but let me tell you more about the sparseness condition in this context. So we were talking about having different scales in the theory. So let me be a little bit more precise about what I mean by theory being sparse. So usually, okay, in many string compactifications, not in all of them, but in many string compactifications, we usually have 3 scales. We have the Planck scale, we have a string scale, an alpha prime, and we have an ADS scale. Okay, so a few slides ago, when I was telling you like, oh, we have cases where the string scale is very close to the ADS scale, when we have like the string-like spectrum, in these situations, the expectations about how the spectrum of the theory will grow is in this exponential way. Okay, so the number of states of conformal dimension delta will go like e to some number ch. This number ch is always bounded by 2 pi. If you have exactly 2 pi in this CFTs, is what people will call exactly Hagedorn. But basically, this number can also be a little bit lower, but still exponential. I will still call that Hagedorn. And this is the growth for states whose conformal dimensions, or basically its energy measured in ADS units, is big, but they're kind of like lying, they're very heavy, but they're not Planckian. So they're states that are very heavy in ADS units, but not quite Planckian scale. So if you have this type of, so this is in the sense in which they're perturbative. So Planck here is what scales with n. So these are states that are down here. But if they have a Hagedorn-like growth, they will still be perturbative, but there will be too much, and they will look more like a string-like spectrum. Okay. Now, what we expect when we have a hierarchy between the string and the ADS scale, so what we hope happens is that, so then now you have a big separation. And so then again, you will count states that are way, way below the string scale, but still energetic from the point of view of the ADS scale. What you expect here is that you can still have an exponential growth of states, but you want this power to be less than 1. So for instance, let me just, it's always good to have an example. So in the context, let's say that you have a QFT. So basically here I'm computing perturbative states in quantum field theory. And so let's say that my QFT is basically the box defined by ADS3 times a manifold of d minus 3 dimensions. And both of these guys are controlled by the same ADS scale. So let's say the typical example will be ADS3 times S3, let's say. So you tell me, oh, count all perturbative states of ADS3 times S3. Then this power gamma, so just doing like computing the free energy of that box will tell you that this power gamma is d minus 1 divided by d. Okay, so it just comes from dimensional analysis. It's not a very like fancy or sophisticated derivation, but you can see how like just even doing QFT on a d-dimensional box, this power gamma, you can have an exponential growth. The coefficient here, CS, of course, doesn't grow with n, so it's not controlled by G Newton or anything like that. But it's always less than Hagedorn. So if you exactly have an exponential here, then it tells you, that's a string spectrum. So an exponential here will tell you have a string spectrum. If you have a less power, you can always think that it comes from some d-dimensional box that gives you that suitable power. So in the case of 6-dimensional supergravity, this power will be 5/6. So that's how many perturbative quantum fields you can fit in that 6-dimensional box. Okay, so this is what I mean by slow. So this will be my connotation of what's having a slow spectrum versus this previous one, which was a fast spectrum if you have like delta. So this is the condition that we're going to impose on the elliptic genera. So we basically want to distinguish between the slow growth on the spectrum. So we'll read off the coefficients, the growth of the coefficients from here, and establish if they fall into the slow category or the fast category. Where this delta here is basically a parameter that is very big. It's taken in the limit and goes to infinity, but delta is not scaling with n. So you're not counting black hole states. You're counting perturbative states, okay? Very good. Now, let's go back then to our classification. So I explained to you the two conditions, and we have these 4 types. So we're going to start putting theories into a bucket. Now, two comments. There's 2 things that you can say about this criterion before even specifying theories. And I want to make those comments. So some of the things that we proved, which are quite nice, is the following. So each of these 2 criterions separately, you can show that you will meet them only if the central charge of the seed, so this theory here will have a central charge that I'm calling C0. Just to be clear, the symmetric product orbifold will have total central charge that is n times C0. So C0, it can be a small number. But in particular, for you to meet either of these two criterions, the seed central charge has to be less or equal than 6. And because I'm doing supersymmetric theories, that's why I'm putting bigger than 1. Okay, so any theory here that you put, any supersymmetric theory that you put here that has central charge bigger than 6 will not comply with those criterions. So there's infinitely many theories that will not satisfy both of these criteria. Most of them will not satisfy this criterion. Okay, so you're bounded by this window of central charges if you're thinking of symmetric product orbifold constructions. From this one, it's easy to see why it's coming from the twisted condition on the moduli. This one, it was less obvious that the sparseness condition required that C0 was less than 6, but it is true and it's proven. Then the second thing, which is very nice, which also involves the mathematics, is that criterion 2 is very systematic to go through. It's actually, if you assume that the elliptic genera does not vanish, it's going to be described, or it's going to be very closely related to a weak Jacobi form. Weak Jacobi forms basically have a ring, and so then you can very systematically say that you have searched through all theories and just from looking at basically the space of weak Jacobi forms. So in some sense, trying to check criterion 2 is something that you can just go, well, this is what we did. We wrote computer code and you just go and check until you get bored all of the weak Jacobi forms that you want to check. Okay, and so, and we gave a very nice criterion, and when this is met or not, so it's just a solvable condition. It's not a mysterious thing to do. And so we gave the systematic steps to check this criterion. Now, the third thing that I want to say is that also it was quite surprising that within the context of criterion 2, so we were distinguishing between fast and slow. So many cases were fast, but every time it was slow, this power that showed up here, which I was calling gamma before, so gamma was always equal to a half, no matter what. So either you got fast and exponential growth, or you got a square root. And those are the only two options that happen within the land of Jacobi forms. There's no other intermediate type of growth. So it's either a half or either one. I don't know physically why that's the case. I just know mathematically why that's the case. In any case, yeah, it's a curiosity. I don't have anything deep to say, but it's kind of curious that it was always like a square root. Okay, but well, but let's talk about the different types now. So what are these different types? So what are we finding? So when we go through and building theories that follow into each of this.
Alejandra, sorry, I had a question. So the sparseness criterion, is that equivalent to saying that if your partition function were a modular form, it would be always a weakly holomorphic one?
Well, this is just elliptic genera.
Yeah. So right. So if you thought of it as a Jacobi form or a modular form.
Yeah. So I'm assuming that the elliptic genera is a weak Jacobi form, which I think I'm allowed to from
yeah.
variance.
Right.
But that's the assumption, which I think.
So criterion 2 implies that assumption. Is that right?
Yeah.
Okay, and that's why you get the exponential. Is that right?
Yeah.
Okay, fine.
Well, you either get, so there's two things that can happen. So if it's slow, it's like this. And then of course, you also have many weak Jacobi forms, which will give you just this. So
Okay.
it falls into those two categories, and those are the only two options.
Right.
And so then it's distinguishing between, does it look like Hagedorn or does it look like a square root?
Okay, fine.
And there's no other like flavor that you can get.
Yeah.
But this assumes that the vacuum contributes to the elliptic genus, so that, and you don't have fermion zero modes. So if you have too many zero modes, then the elliptic genus vanishes. So that's only like, so of course, if the elliptic genus vanishes, then I don't have anything too interesting to say for obvious reasons. And then, yeah, that the elliptic genus, it's a partition function, it's a modular partition function. And the algebra, the Virasoro-Katsumudi algebra tells, well, just a CFT type argument of like, oh, why are partition functions modular and covariant or invariant? It just relies on that. On like, do we believe that objects, partition functions, and 2D CFTs have some modular invariant properties? That's what I'm assuming. But yeah, but the only cases I'll mention later on, it's cases when you have n = 4 supersymmetry. You still have this restriction that the central charge has to be less or equal than 6. But if the elliptic genus vanishes, then you have to look at the generalized elliptic genera. And then it's not quite, well, it's still a Jacobi form, but it's not weight 0. And so then, yeah.
I see. And you're not, at this point, you're not thinking of it as a holographic CFT or something. At this point, it's just.
No, I'm just classifying. I'm just saying.
You're just classifying, right?
You have the states of like weak Jacobi forms. Let's come up with like, when do they obey this versus when do they obey that?
Okay, good. So you haven't told me what e raised to delta means, but okay, right, correct.
Delta, it is the conformal dimension in the NS sector. Or well, is it the discriminant of the state in the NS sector?
Yeah, it looks like it's much more bigger than, I don't know, a black hole entropy, for example, right?
Oh, but nothing of this scales with n. So with G Newton.
Oh, this is just the. I see what you mean.
But it's just the energy. So if you had a black hole here, then you would have written down like C times delta.
Oh, I see what you mean. Okay.
So then that's why it's much less. This is why these states are perturbative. They're not growing with the Planck length. So nothing here is scaling with G Newton. So that in that sense, that's what I call light. None of these energies, and none of the states that I'm counting are states whose energies are comparable to G Newton or to n in this language. These are all states that can be very large, but scale like n to the 0. So they're the polar states, if you want. It's the polar part of the weak Jacobi form, and I'm taking the limit when the polar states are very, very close to their, they have very, very large discriminant in some appropriate units. But yeah, so they're the polar states.
Sorry, may I also ask a question? So this gamma was related also to the dimension of the spacetime, but this is of course a lower bound, I guess, because it's the elliptic genus. So, but that means I think this lower bound is much lower than what you would expect for any.
Exactly, it's super low. It's really, really low.
You have a lot of cancellations. Is that what it means in any case?
Yeah. So in the case, so if you have ADS3 times S3, then gamma, if you are looking at the partition function, you should expect 5/6. Then Nathan actually did an estimate of just the quarter BPS states. And the quarter BPS states were, I always forget, I think it was 3/4. So it's lower, but not quite as low. And yeah, but if you look at the elliptic genera, it's a half. So yeah, there's a lot of cancellations for K3.
Yeah, but in general, I mean, even because I guess the dimension that you would need to get 1/2, what is it, 2 to that, which is kind of impossible.
Yeah, but it's kind of like stupid because it would mean like from the point of view of like, how did I write it? Like, sorry, it means that you have like a negative internal manifold.
But that means that in any case you always have a lot of cancellations in the
Yeah. So either you have tons of cancellations and you get the square root, or you have like almost no cancellations and you have Hagedorn growth. So, which is a little bit disappointing because we thought that the elliptic genera will give us some information about what the internal manifold could be. We were excited. We were hoping like, oh, maybe we're going to get like different powers and then we can say something about what this internal manifold might be in these cases. And no, it has no information. So it's very disappointing. It's yeah, it's very hard to extract information about what this is in these situations. So yeah, for the case of K3, it's only the R symmetry that tells you that you have an S3 if you wanted to be very crude.
You have information about the fact that you do expect that a lot of the guys, the fraction of states that cancel in the elliptic genus, in a sense, right? They have a lot.
Yeah, but
it's not just a priori, right?
Yeah, but I wanted to know more. So yeah, but what we learned is that a lot of them cancel, and it's like, okay, great, a lot of the things cancel. Okay, so but let me. So where was I? I was here. Okay. So okay. So in these 4 types, as I go, I'll show you very concrete examples of these 4 types. I'm not going to show you all of them because you will be bored, and I'm running short on time. And clearly, I'm not going to go through the deformation part. As I noticed, I always run out of time on these things. Okay, but it doesn't matter. The classification is still, it's very beautiful. So the thing that I want to highlight here, so type 1, which is where you have both criteria satisfied. They're the most interesting example from a holographic point of view, but they're actually, there's a sense in which they're not very easy to find. Okay, so that's why we sometimes call them like needles in a haystack. Type 2, they are the ones that are giving me a headache. I think I have, yeah, there's my little ghost. So type 2 are the strangest things because you do have a moduli, and I'll show you also why I'm so confused about this type. But the elliptic genera, if you compute it, it has Hagedorn growth. So yeah, not my favorite. Type 3 is the boring one, so nobody will care about this. So they're the ones that don't have moduli, so there will be no supergravity. Well, they don't have a moduli in the sense of being twisted and single trace. They can have other marginal deformations, but not the ones that will do the tricks that I want them to do. And the elliptic genera is Hagedorn, so we don't really care about those. Are yeah. And then the other ones that would be really, really counterintuitive, which we call the unicorns in the classification, we have not found any example that complies with it, but it will be one where the elliptic genera displays slow growth, but there's no moduli. So you will have tons of cancellations, but then there's no thing to deform to. And so why are you having like the slow growth? Like it will be it will be kind of also very bad from the point of view of what are necessary conditions to build a holographic CFT, because it will tell you that the elliptic genera really doesn't tell you anything about a strongly coupled point. There could just be cancellations by accident. Okay, so far what we have found is that at least every time that you have cancellations in this way, there's always a moduli that is single trace, twisted, half BPS, which is great. But the opposite we haven't found. But okay, but we do have some strange ones. But in any case, let's go through some examples. So type 1 examples. So there's a whole infinite family of theories that are of type 1. And they're basically when you put in one of these instances here, an n=2 Virasoro minimal model. So pick any of your favorite n=2 Virasoro minimal models, do a symmetric product orbifold of it, and it will be type 1. And to show you a little bit how the moduli looks like here in this table, which is in one of our papers also, I'm illustrating so that the moduli that I care about, the one that I'm emphasizing here is this last column, that is single trace and twisted. But also just to illustrate, you can also have other type of moduli that these are multi-trace moduli, and these are just untwisted moduli. But the one that we want to deform by is this. And the thing that is also interesting is that usually in the case of D1, D5, it's twist 2, but you can also have other instances where you have twist 5, 7, 3, 4. Okay, so all of these examples obey that they have an exactly marginal deformation and a sparse spectrum. Now, let me give you some examples of type 2 and type 3. So here's a table with type 2 theories. So the way that we found these other very counterintuitive examples was by doing the dumbest thing. Is like, instead of taking a single minimal model, take tensor products of minimal models, and then and that's a different space of theories that increases the central charge, and see how do they comply. So tensor products of minimal models are not necessarily type 1. There's many of them that are type 2, so it means that they do have a moduli, and here we're describing what the moduli is. But if you look at their elliptic genera, they have Hagedorn growth. And then there's also lots and lots of theories that are type 3, where they neither have a moduli nor they have this slow growth. Okay. Now, just to give you a little bit of a comparison why the type 1 were like needles. So, this is also, it might look at as a counterintuitive table. So here we listed type 1 theories that are built out of tensor products of minimal models, just to also see, like we basically did an entire classification of any time you had tensor products of minimal models. And also, it doesn't have to be just 2 copies. We went through 3 copies, and well, then you stop there because 4 copies, the central charge goes above 6. But in case, I do want to illustrate, this table looks bigger. So you might have said, oh, there's more. But no, be careful that it's only for very specific values of K. So they're quite like rare. And so you just specify specific values of the tensor products for which you get type 1. But these things are way more generic. It's just that we could write the conditions more succinctly. And there's way more that do not comply with a slow growth condition. Okay, so it was kind of, it's more difficult to find these. And so you have to look at very specific values of K to satisfy this. But then very generically, you will get one of these 2. Okay, just by chance. Now, all of these things are like infinite spaces of theories. So it's hard to quantify infinity against infinity. But I do think that, like, yeah, there's a more discrete set of values here compared to the values, the ranges of values in this other case. Okay, so just to illustrate that these are more rare, and these are quite generic within our classification. Very good. So summary. So what have I done so far? So we've been exploring the space of theories of symmetric product theories C here, labeled by their central charge C0. If the central charge is bigger than 6, they always will be type 3. They will not satisfy with neither of these criteria. If the central charge is between 1 and 3, this is where the Virasoro, this n equal 2 Virasoro minimal models fall. They're all type 1. All unitary theories are type 1. We only include cases that are unitary and compact. But within this range, which will be the interesting range between 3 and 6, you find the 3 different classes. Okay, and just to reinforce, some of these comments have gone passed through. Yeah, we only consider theories that are unitary and compact. We assume that the elliptic genius doesn't vanish. Just for reference, D1, D5, it's sitting right there at the edge. C not equal to 6. And then, yeah, this is exhaustive. We completely search every single, because the minimal models range all possible theories for with n equal 2 supersymmetry. But here, of course, we do not know what all supersymmetric theories are, but we've been trying to systematically go through some of them, and we have found examples of 1, 2, and 3 within this range. Okay, very good. So now I think the only thing I'm going to say about the deformations, because I don't want to fully use the hour nor rush through this, is to let me just highlight why am I so bothered about type 2. And in contrast to type 1. So I'll just skip to the table. So Yilda, one of my students, she made this table for me because I was very upset. So I told her, like, hey, show me some list of examples when the seed central charge is 5. Like, tell me so far what have you done? Like, what type of theories have you found? These are not all the theories with the C not equal to 5, but just to have some idea of like what's going on. in this classification. And so she wrote down when the theory was sparse and when did it had a moduli. And then here is a description of the composition of the moduli, where basically this is telling me the number of times that you see a number repeated is what is the twist. And then 1 means that it's on the ground state of one of the copies, and 8 mean that it's built out of like a primary field on the other theory. But in any case, so it's information about what is this moduli, this deformation, a single trace twist deformation. Now, in this theory, there's a lot of different examples that you can focus on, but just for concreteness, let me highlight these 2 that I highlighted here. So this is an example of a type 2 theory that it is not sparse, but it does have a moduli. And this is a type 1 theory that is sparse and does have a moduli. The reason why I'm highlighting this too, and why I'm like, I don't get it, is that the moduli also, if you look at its composition, basically the same. So the thing that I'm bothered about, I'm sorry that I'm like, I know that nobody is like, why is she like raising her voice about this? It's like, because I'm really upset that the moduli, I thought at some point, oh, there will be a different structure to the moduli. So if I start deforming by it, one of the guys, like in this case, this moduli, I will be able to see that the moduli would not lift many states. And that's why you still have Hagedorn here versus here, but the moduli is really, really similar. So it's basically the same, roughly speaking, the same operator that in both cases. And then my student Susana did a bunch of computation, did way too many computations trying to see what happened to a lot of like the holomorphic operators in this theory. And so with this, I will end. I will not show you. We'll go through this, and I'll show you my sad face. There's my sad face. There was no difference. Like if you did a deformation in these cases of a type 1 versus a type 2 theory, there's just no difference. But both of them, like there's many states that acquire anomalous dimensions, and even sometimes their magnitudes are the same. And so do I care that the elliptic genus was very sparse or not? I don't know. But there is something that is lowering, that should be attributing to, in one case, having a lot of cancellations, and in another case, not having those cancellations. Because the Hagedorn growth here tells me that a lot of these quarter BPS states persist throughout moduli space. So why are they persisting? What is the physics here? I don't know. Any case, that's where I'm upset. So let me just wrap up. So yeah, we didn't do anything about the deformation. If someone has questions about that, I'll be happy to answer them. But in any case, we went through these 4 types of criteria. We have examples for each of them. I want to be very explicit that these are very systematic and tractable examples. They're very explicit CFTs where you can do like any computation that you want. They can just be technically very challenging, but they're quite precise. And the examples that might be useful for a holographic context are these type 1 symmetries, where we basically have a sparseness condition in the elliptic genera, and we have moduli. And the question is, do they really lead to something that is holographic or not? Like, are these conditions sufficient to claim that you have a holographic CFT? And if they're not sufficient, what else should we be imposing on the symmetric product orbifold to lead to a holographic type theory? So with that, I'll just leave you with this nice slide that shows some of the next steps and what I think are the important questions as you study the space of conformal field theories. So I'm done.